Hello, everyone. Welcome to a guided tour of AI and neuroimaging. AI means artificial intelligence. And for the next hour, I'm going to give you a little bit of an overview of all the major artificial intelligence methods that are being applied today in neuroimaging. And this talk is for people that are new to this and also for mathematicians and computer scientists who are expert in these methods. So a summary of today's talk is to go over how AI is used in neuroimaging today. I'll tell you what the main methods are to know about, from 3D CNNs, which are convolutional neural networks, to vision transformers, generative adversarial networks, diffusion models, VLMs, which are vision language models, and also federated AI. We'll talk a little bit about what we need to be careful of. So when you use these methods, there's a risk that they'll lock onto features that aren't important, something called shortcut learning. Domain shift, which is a problem that arises when you apply an AI method to data that it has not been trained on that may be quite different, resulting in some poorer results. And then also algorithmic fairness, making sure that these AI methods work well for everybody. Some hot topics we'll cover include automatic diagnostics in radiology, using explainable AI, where the AI can help us see how it's making a decision. Generative AI, which is used for anomaly detection or disease detection or even quality control. But that can also be used for enhancing images and creating new kinds of images. Really exciting work that will show creating PET scans from MRI scans and other novel applications of generative AI. There's also AI that learns from multiple data types. So you can use imaging and genomics and query those images with text using something like ChatGPT, and we'll talk about those. And finally, we'll talk about adapting AI to other types of neuroimaging data, diffusion imaging, which can be used for tractometry in conjunction with AI, and also functional brain mapping and even mind reading. So the main use of AI is to make predictions. And so you can imagine all of the aggregated biomarker data from patients on the left might consist of genomic data, blood markers, proteins, brain images, even real-time data from watches or actigraphy machines. And you might want to develop a very accurate mathematical model to discover the best predictors of a person's diagnosis, their prognosis, which treatments they should be taking, or their treatment response. And AI and deep learning in this context means creating a mathematical model that may be very, very complicated, that discovers the best features on the left to help you with the tasks on the right. And there are two reasons to do this. One is if you want to actually make the decision, which is an important use of it. And the other is for scientists to discover features that help in making the decision. So an AI method is not just a tool to use, it can also be used to discover important indicators in those health markers over on the left. So deep learning methods include convolutional neural networks, CNNs, vision transformers, variational autoencoders, generative adversarial networks, latent diffusion models that have become very, very popular recently. And all of those are typically applied or can be applied to images, either photographs or medical images. And then there are different types of AI that were developed to handle sequences. So text, sequences of words and sentences are examples of sequences that these are being applied to. Recurrent neural networks, an example being long short-term memory networks, LSTMs, and also transformers that are the basis of the ChatGPT suite of tools for language understanding. So if you imagine trying to develop an AI system that identifies the person on the left, let's say she's called Sarah, we could train such a system on lots of images, photographs of Sarah, and really ask the machine to identify features. It might be low-level features like edges or things that have to do with the intensity of the image, or composites of features like the positions of the eyes and the positions of the nose and other things like that. And the deep neural network will identify these by having enough data to rule in or rule out features that are good, and then making a prediction, which in this case is the person's name. In medical imaging, the same concept is adapted, where the input is a medical image. There's the MRI on the left. And you would train a deep neural network to identify something simple like the person's age, just to test it, or whether they have a diagnosis of something like Alzheimer's disease or some other pathology. It might be amyloid or tau or vascular disease. And you might want to run this to see if the patient's eligible for a certain treatment. So lecanemab, for example, is a treatment for amyloid accumulation in Alzheimer's disease, and you want to know beforehand if people going to get that were amyloid positive. So such a task can be done with a neural network. Now, over 25 years ago, my first student, Alain Petiot, who's now a director at elixir.com, was trying neural networks to identify a part of the brain called the corpus callosum. And he was essentially doing something that would be called today radiomics, where he was defining features that he thought could be useful and having the network sort or prioritize or weight these to label pixels that were inside the corpus callosum. Interestingly, our collaborators at the engineering center INRIA disliked artificial neural networks, or at least some of them, because they said, well, how can we see how it works? There's no simple analytic model. At the time, variational methods and PDEs were being used to segment things where you deform templates to stretch them onto the structures of interest. And there was a lot of interest at the time in trying to define analytic equations that would find these structures and not so much black box solutions like deep learning and neural networks. But in the more recent past, there's been a huge resurgence of deep learning. So this method by Xiaogan Yan and Bin Lu at the Chinese Academy of Sciences was trained on an enormous data set of MRI scans from Alzheimer's patients and controls. And they were able to classify in data that the network hadn't seen Alzheimer's disease with over 90% accuracy. And they pre-trained this on a sex classification task where you were just trying to tell if someone was female or male. And I'll tell you a little bit about these different terms, the names of the CNNs and what pre-training means. Another application that here has been developed by Duygu Tosun at UCSF is to try and predict the pathology that a person has in their brain based on their neuroimaging. Now, if you have post-mortem data, you can see a number of things that aren't detectable on in vivo neuroimaging. And if you have both pre-mortem and post-mortem data from somebody, you can try and train a network in here, in this case, a random forest network, to infer whether there are different types of molecular pathology, Lewy bodies, T43, cerebral angiopathy, and these can be trained with really quite excellent accuracy. Another use, which you might not have thought of, is AI that reads brain scans shows promise for finding Alzheimer's genes. So if you could classify whether someone has Alzheimer's based on their brain scan, you could run this on a massive database of maybe 100,000 images, and then run a scan of the genomic data in the same people to find markers that are linked to Alzheimer's disease. And this would be extremely efficient. And there's an article there about how to do this. This work by Andy Sakin and Taiho Zhou at Indiana University essentially finds in PET scans the most predictive features. Here, tau-sensitive PET. Tau is a Alzheimer's pathology. And then the CNN in this case lights up the part of the image that have features that predict Alzheimer's disease. And then this, in a second stage, can be fed into a neural network that looks at the genome. So he also, Taiho Zhou, has a method called SWAT CNN that slides a window over the genomic data and uses feature detectors in a CN to learn patterns in the genome that then might predict not just Alzheimer's disease, but also the things going on in the image. Now, you could say, do you need a lot of data to train these methods? Will we ever have enough training data to make them perform well? And there's something called scaling laws, also known as power laws, where people try and investigate how the deep learning accuracy depends on the amount or diversity of training data, the amount of time on graphical processing units, which are typically used for training these models. And this depends on the task. So the model architecture matters. CNNs, vision transformers, which we'll talk about, matter in how accurately the task can be done and how much training data is needed. But it also depends on the ingenuity of the developer. So we'll talk about pre-training tricks, fine-tuning foundation models, using generative pre-training, which I'll explain. But it also depends, the accuracy of the methods depend on the diversity and use of the training data. Curriculum learning, for example, visits the training data in a certain order, either preferring difficult to classify examples first or saving them till the end. Adaptive learning picks data that might be the next best choice to have a look at in improving the algorithm. And reinforcement learning, such as is used in automatic cars, uses the incoming data to decide what to do, and then you can go and seek out training data that's most optimal for performing a task. And all the time performance depends on identifying domain shifts and confounds that might be giving over-optimistic performance. Now, in genetics, the question arises, how much data, how many people do you need to collect data from? In this case, to discover genetic variants that account for genetic risk for disease. And it's been found that you might need data from 10,000 to 10 million people to find all of the genomic variants, at least common genetic variants that account for genetic risk for these diseases. But you'll see that the diseases differ in how many people are needed. On the x-axis, it can go from a few hundreds of thousands to millions. And so that same question is of interest in deep learning. And this is a nice paper in genetics by Dominic Holland and Anders Dale. A lot of it depends on whether there are any strong predictors or only weak ones and what trait we want to predict, and even if the predictors are relevant to the question that we're looking at. So here's work by Nikhil Dinakar in our group, where he tried to classify MRI scans as being from patients having Alzheimer's disease or healthy elderly. And the performance on the y-axis increases with the more training data. By the time you get 2,000 MRIs, you get almost 90 or over 90% accuracy in diagnosing disease. But the methods used, you'll see here, differ. And so some of them are very simple. They use something called radiomics. Others use neural networks that look at 2D slices, and others 3D. And we'll talk a little bit about what those different methods do. So Nikhil and colleagues benchmarked dozens of AI networks for detecting Alzheimer's disease and related dementias from MRI. The best ones were so-called vision transformers, SWIN transformers. We're testing a lot of these in our Enigma neuroimaging network right now, with a goal of creating a sort of superglue type benchmarking system. So for those of you familiar with superglue, it's used to test large language models, how well they answer questions, how well they understand sentiment. And you can imagine with neuroimaging, you would have a similar benchmarking system that ranks these different methods. And just to say, these are already used. So the FDA has approved a number of algorithms for detecting disease based on neuroimaging. And so it's a very active market in radiology. So just to talk about how a convolutional neural network works, the input on the left can be a 2D or 3D image, an MRI scan. And then on the top right, through a series of mathematical operations, this input data from multiple people is passed through layers. And these layers compute mathematical functions of the input. They might be convolutions that apply feature detectors to distill useful features from each layer. And there are also pooling operations. So to avoid this getting out of control in terms of the memory requirements, often little 2x2 squares in the input, the maximum of the features in that 2x2 neighborhood is saved and put in just one pixel. And so you'll often see as things go forward in a neural network, the actual size of the image gets reduced for reasons of economy. And to train this, you show the network training data and the output that you want it to give. And you compute the function in a forward pass. These nodes are mathematical functions, usually with weights and biases and nonlinear activation units. And during backpropagation, the error of the neural network is calculated, and the tuning of the network parameters is applied that maximally reduces the error. And so you pass the training data through the network many, many times, and then it's regarded as achieving convergence when the error fails to decline on a held out validation data set. And so this is repeated many, many epochs until the validation set error no longer decreases, and then you can use it. So this has been applied in classification or detection of epilepsy, Alzheimer's disease. And you could ask, well, could you have the machine tell us which features it's been using in all of these different deep learning layers to try and understand what it is that is important for predicting or differentiating these different neurological disorders? So one such approach that is illustrated in this nice paper by Eric Kastner on epilepsy lights up the regions that were useful in detecting whether a person with temporal lobe epilepsy had a seizure focus in the right hemisphere or the left hemisphere. You'll see sometimes those features are in the hemisphere that the seizures are beginning in. Some of the time, the hemispheres are compared. And if you want to get into this, there's a very nice book called Interpretable AI there that goes into methods such as occlusion sensitivity analysis, Grad-CAM, layer-wise relevance propagation, and something that's used with transformers called attention flow. So just to tell you about one of them, occlusion sensitivity analysis, when you've trained a neural network, when you're using it, you can cover up patches of the input. And so if you have an image over on the left, you can go around the image and cover parts of it up. And you can measure the degree to which its performance is impaired by covering up the different parts of the image. And so this could give you a relative importance map for each region. There's a couple of pitfalls with this. So some neural networks are trained using something called dropout, and they're also trained by giving inputs that are occluded to make them robust to this type of sensitivity. So obviously this only works if you've trained a neural network without those techniques to get around the drop in performance. This occlusion sensitivity analysis can give you salience maps. So let's say you are training a classifier to tell if a photograph contains a dog or a cat. Just covering up regions of the input image and seeing how much difference they make can be shown here to reveal which areas of the image, here the dog's head, I suppose the dog's feet, that make a difference. And you can build these up as a saliency map to help you understand what the network is using. Now, occlusion sensitivity analysis can also be used in video data. So you can say, find all the videos about boxing, and you can train a neural network to find videos that are linked with boxing. And if you run occlusion sensitivity analysis, it will give you a saliency map that picks up sensible things. Here's a very nice paper that shows how to do that. Now, another approach for interpretable AI is called gradient class activation mapping, or Grad-CAM. And this actually goes further into the neural network. So it looks at one of the later layers of the neural network, usually the last one, and it says, in this later layer of the neural network, which presumably has aggregated all of the relevant information for the prediction, what is the dependency of the output on these different areas? And so at the very last layer of a neural network, you still have lots of feature maps. They might be high order features. But as you see there at the bottom, you can say, maybe the texture or maybe the brightness or maybe the presence of certain objects matters. And you can get an overall picture of what mattered in this instance for saying that that dog on the left is an Australian Terrier. Now, I'll skip this. This is just a detail of the method. This works very well for photographs. And so if you want to say, if a picture contains a cat, Grad-CAM will tell you which parts of the image were relevant to that. Or a dog, it finds the dog's face. People brushing their teeth, it finds the toothbrush and obviously what they're doing. And even things like cutting trees, it can find things that we would regard as useful for those tasks. So let's see if it can work with brain images. So one problem with Grad-CAM is that when you apply it to detect, for example, brain tumors, so to a network that's been trained to do this, the resolution is limited by the spatial resolution of the last convolutional layer, which for the glioma on the left might be fine, but for the pituitary tumor on the right might be a little bit too uncircumscribed to be of any use. So one variant of this is multi-layer Grad-CAM. So you go into the convolutional neural network, you do a gradient sensitivity analysis at each layer, and because the first layers have fine scale features and the last layers have large scale features, you can integrate and combine these saliency maps or even look at each one. Now, this paper by Qiuhua Lin and Vince Calhoun applied this to functional brain mapping data. So what they're doing is they train a CNN, in this case to detect schizophrenia in people's functional brain maps. Once the classifier has been trained to good accuracy, they then go and look at the feature maps at different layers. And as you can see here, deeper layers seem to emphasize activations in the default node network, which is important in schizophrenia, whereas earlier layers find the edges of these networks. And so you could use this as a discovery principle to identify features of the brain that matter for a particular illness. Now, I mentioned earlier that different convolutional neural networks in particular might have different accuracies, either ultimately or with limited test data. So we'll talk about what matters there. This is based on a paper by Nikhil Dinagar in our lab. So you could use radiomics. So that means you just define some features in the image, maybe the texture, the edge strength. It could be something about the histogram of the image. And rather than have the convolutional neural network identify these features itself, you just combine them using any machine learning method, even a random forest classifier would be fine. This is 72% accurate in detecting Alzheimer's disease. It's not bad, but we can do better. If you have the neural network discover features itself, here's a CNN that's trained on 2D slices, it'll do a better job. So this is now 78% accurate in detecting Alzheimer's disease. Because 2D images are being fed in, there has to be a way of combining the opinions of the CNN on the different 2D slices. And you can do that with a recurrent neural network here in LSTM with a rather amazing architecture there in the middle. These were invented to handle text or sequences of words, but they can also handle sequential data, and this does relatively well. DenseNet is a convolutional neural network that essentially filters data at different layers, but rather than throw the earlier layers away, it concatenates them with the later layers so that all of the multi-scale information is available for making a prediction. These are extremely good, 91% accurate at detecting Alzheimer's disease, very, very good performance. And there's been an evolution of these two. So initially, CNNs had successive convolutional layers. ResNets included skip connections, which avoided a problem in training CNNs where the back propagation would get stuck. It wouldn't be able to communicate updates to all of the layers. And now finally, DenseNet, which is probably the best of all, concatenates all the features and makes them all available to make the prediction. A different class of deep learning methods, transformers, is used for encoding text. So adapting these to images, you can split your image up into patches, just like words in a language. And you can feed them into, in this case, a vision transformer and have it classify Alzheimer's disease. And it actually does pretty well. It does better, particularly if pre-trained, than the other methods that we've been talking about. Now, I keep saying pre-trained, and what does that mean? So suppose someone has developed a neural network that works really well at classifying objects in photographs. You'll often find that that so-called foundation model is adapted to handle medical data. And so what they do is they freeze the weights or the settings in the earlier layers, and they only tune the later ones. And this gives you very, very high performance in cases where there's only limited data, medical data to train it on, based on the premise that the features that it's detecting are somehow generic. So you can get a DenseNet that distinguishes COVID from viral pneumonia with almost 100% accuracy if you fine-tune a network that has been trained on photographs. So what does it mean training a neural network on photographs? Well, fortunately, since about 2010, there's been a database of photographs that computer scientists have been looking at. Basically, ImageNet consists of 14 million hand-labeled images with about 20,000 categories of objects. A typical category, such as a balloon or a strawberry, might have several hundred examples of images. And you can see that over the course of time, the accuracy, which is shown on the y-axis, went up. And this was a competition. And so AlexNet, which is a very deep neural network designed by Alex Krzyzewski, essentially computes features that we would think are fairly generic, the ones that you see in the little box there. And this has led to the adaptation of things like AlexNet for medical images, because you can imagine training these on millions of images has led to some quite stable predictors. So one of the things that you can do with these prototypes is you can say, how long do they take to train? How much compute time do they need? Does their accuracy depend on the number of parameters in the neural network? You'll see some network CNNs called VGG19, which have a huge number of parameters, but actually quite slim neural networks with fewer parameters, which are more efficient to train, can do better. So often these prototypes are fine-tuned for medical imaging tasks, and we'll talk a little bit about that. So this architecture, VGG19, VGG stands for Visual Geometry Group, and 19 stands for the number of convolution layers. You can imagine that over the course of time competing on these photographic databases to get the best accuracy in labeling the things in the photographs, people adapted these in various ways. I mean, there's no limit but people's ingenuity and time to explore these. This one did particularly well. Sometimes you see these networks shown like this, where each little brick is a convolutional layer and the features that come out of it. And when it's labeling an object, in this case a fox, you can see what types of image the layers are most responsive to, and they tend to be higher and higher order features. So if you want to train a medical CNN, you have a couple of decisions to make. One is that brain MRIs are usually 3D, not 2D. If you do functional MRI, they're 4D. So you could stick with 2D CNNs and feed in slices, or you could use 3D kernels. You could adapt the idea of convolution to 3D and use a 3D kernel, but then you'll need more memory. And then conversely, you might have to pass smaller amounts of data through the neural network. You could just use ImageNet, or you could pre-train your neural net on large brain MRI data sets. If you do, you might want to pick a task such as predicting the person's age or sex, which there's a lot of data for. And the final type of training, which we can talk about, is contrastive learning. This is self-supervised learning. So you don't even train the neural network to recognize objects of different kinds or diagnoses of certain kinds. You just tell it to organize the embedding of the data that's used for classification such that similar objects are put closer together. And I'll tell you a little bit about that. Contrastive learning is one of the better approaches for training neural networks. And what you do is if you have input data such as the ones on the left, you can essentially augment the input so that you change the contrast or the brightness of a certain type of image. And you compute embeddings that put all of the similar things close together in the embedding space and all of the different things further away. And there are different mathematical functions that will help you to separate and disentangle the different classes before you go ahead and do classification. So this is very cool use of data that you can do before performing classification. The final way of training neural networks is using generative AI. So this rather wonderful paper by Walter Panaya and George Cardoso and colleagues makes synthetic brains. So let's have a look at that. So they start with random noise, and they will make a synthetic brain. And doesn't that look wonderful? This is a slightly different approach called generative AI, which I'll talk about in a minute. But you can imagine if you run out of training data because there's not enough MRIs, you can make some. And this method allows you to create brains with prescribed ventricular size or brain size, brains that match a certain age and sex. This is trained on a vast amount of data. This is the UK Biobank. And it's a slightly different type of AI, generative AI model called a latent diffusion model, which we'll talk about next. So McKay is a conference that has tutorials on these methods. If you're wanting to go into greater depth, you can go to their tutorial on diffusion models, which is the first type of generative AI that we will talk about. So generative AI does not take an image and tell you what it is. It will take an image or something else and make a new image or a new type of data. So the goal of generative AI is to take a set of training data and understand that data so well that it can produce new examples with the same statistical properties. So it could generate faces or images that are realistic. Now you could say, well, how does it do that? So one such approach for generative AI is called a variational autoencoder. So what this does is it takes a lot of images, it pushes them through a neural network that simply outputs as good a version of the original image as possible. But there's a certain penalty here. So you run all of this data through a bottleneck. That very slim layer in the middle maybe only has a very small number of parameters. And you'd like to essentially compress the input data so that you can still reconstruct the input to a high degree of accuracy, but you're using a much smaller number of parameters in the middle. So this is probably familiar to you in the context of image compression, where you replace the input with a compressed data set. Now, how is this compressed data helpful? Well, if you look at handwritten digits, this is the MNIST data set, you can use a variational autoencoder to encode all of the complexity of those handwritten digits on the left and arrange them nicely in an organized way so that all of the digits that are the same lie in the same part of the latent space, the embedding space. And this so-called latent space or embedding space is spanned by the parameters in the middle bottleneck layer of the variational autoencoder. A standard autoencoder, so you might be familiar with other methods to do dimension reduction on high dimensional data. T-SNE and UMAP come to mind, so T-distributed stochastic neighbor embedding, or T-SNE, and also UMAP, which is uniform manifold approximation. They will take very high dimensional data like images, and just like the image on the top right there, they'll embed these into clusters so that you can view all the data in 2D and work with it more effectively. But what a variational autoencoder does is it maps all of that input onto a multidimensional Gaussian, so essentially a normal distribution here in 2D. And you'll see that this has been caused to embed the images on the left into a space where all of the digits corresponding to 7 sit in a certain part of the latent space. All of the digits that are number 8 are separated and they're somewhere else. And you could say, well, this is very useful. I can go into that latent space and go and tell you what digit was written. And not only that, you can sample from it. So by going into that nicely organized latent space, which is a 3D Gaussian or 2D Gaussian, you can think of a Gaussian variable, you just generate one, and go make an image. And when you train a VAE, you force this embedding to have two properties. One is it has to be able to reconstruct the output with as close a smaller mean squared error as possible. But also the embedding has to be as close to a multidimensional Gaussian as possible, ideally with a diagonal covariant structure so that the latent factors are independent. And you can train this neural network to make these embeddings to satisfy those two criteria. And the principle behind this is shown here. Now, the objective of a variational autoencoder is shown there at the bottom. It's the sum of two terms, one which encourages the embedding to be multidimensional Gaussian, which is enforced using a Kullback-Leibler divergence term between the latent compressed vectors and a multidimensional Gaussian. And also, you would like it to reconstruct the data that you began with as closely as possible. So in the formula at the bottom, for Gaussians, the SKL turns into a sum of logarithms, and the reconstruction loss over there on the right can also be optimized. Now, this works very well. So once a VAE is trained, you can cover up some of the image, input it, and ask it what the output is. And it's a bit of a miracle, really. It will in-paint areas with a fair degree of realism. I mean, if you look at this very carefully, here's an image of a concert going on, and when you put it through the variational autoencoder, it will estimate its best guess of what is going on in the background, and there's a bird that has also been in-painted or interpolated very well. So why does this look so much better than other in-painting methods? PCA is one-dimension reduction method where if you're missing data, you can use principal components to reconstruct the missing data, but it doesn't do quite so well. One reason it does well is that an extra reconstruction loss term can be added when you train these. And so let's look at a face generator. If we read the Celeb A dataset in on the left, which is various pictures of faces, and you use a variational autoencoder to sort these faces on the right, you can add a term during training the VAE, which is the perceptual loss. Now, what is the perceptual loss? Well, you run all these faces on the left through that VGG network that we talked about earlier that identifies objects. So the idea behind this is, if something really looks like a realistic object, the network layers in the VGG network that can label objects should have a reasonable output. Those network layers that interpret objects, they should be, in a sense, typical of real objects. If you are synthesizing images that aren't very good or they're too blurry, the VGG neural network, which labels objects, will say, well, this really doesn't look like anything at all. So you can use the VGG object labeler as a critic, or essentially an evaluation of whether or not the synthesized images are reasonable. And if you look here, VAEs trained just with a pixel by pixel loss are very blurry, but those that have been helped by the VGG network to create realistic images using the perceptual loss are much, much better. Now, if you run these neural networks on faces, you'll see that all the faces looking right are at the bottom, looking left are at the top. There's a cluster of images that are female faces with blonde hair. So this is really where things started to happen, these deep feature consistent variational autoencoders that enhanced not just SKL terms for latent space Gaussian sampling, and not just pixel accuracy, but also fidelity to natural images that was arrived at by using the VGG object detection neural network. So this can generate images from random Gaussian noise. You can go into the latent space, make up a random vector, and pull out something that looks like a face, which is great for sampling new images. And so you could say, well, can it generate brains? If I feed in a lot of MRIs at the top left, can it make brains according to my specifications? Now, it'll certainly make brains, but in brain imaging, we might want to say, can you make brains of people of a certain age and sex, or with a certain disease, or with a certain ventricular volume? And these papers on the bottom show you how you take a generative model and you add conditions. And so you don't want it to generate just anything. You would like to condition the generation on some property, either a certain age or sex, so that the outputs are consistent with people of that age or sex or certain characteristic of the brain. Now, the resulting outputs are fabulous. And so I glossed over the fact that the decoder for these generative models is something called a UNet. A UNet is a type of CNN where the far side of the CNN has very, very fine scale features that it creates. And you can say this is from Walter Panaya and colleagues' paper. This is really hard to distinguish from a normal brain. But this is a brain of nobody. It's a synthetic scan, doesn't belong to anybody at all. Now, in this paper, they describe using the hybrid conditioning approach, we could condition our models and generate brain images where we can specify the age, sex, ventricular volume, and brain volume. And it's based on a paper by Rombach, which is cited here. So I'll tell you what is going on. So first of all, if we don't condition images on anything but the input, it's already useful. So if we put in an image of someone with a tumor or a lesion or something like that, but the autoencoder has only been trained on healthy people's images, it'll find the reconstructed output from its training data that's the closest. But because it hasn't seen any brains with tumors, it just finds the closest looking brain, a so-called pseudo-healthy brain. And subtracting the input from the output in this case can be used for anomaly detection or localization. And this can be done either with a variational autoencoder, which is pretty simple, or a denoising diffusion probabilistic model, which we're going to talk about next. So generative AI in 2024 doesn't always use variational autoencoders. It uses something called diffusion, denoising, probabilistic models. And just to show you how good these are, there's a company that developed this video generator called Kling. There's also one from OpenAI called Sora, where you could say, I'd like to see a picture of a gentleman or a little boy eating noodles or a hamburger. I mean, I would defy you to say that this is actually a synthetic image. It looks just like it's real. So how have we gone from these autoencoders that were only moderately realistic to ones that could fool anybody? And the idea is to use something like a VAE to embed the image data, the training data. But in order to model the data distribution that we'll sample from, we're going to use something called a diffusion process on probability distributions. Those of you familiar with statistical physics will recognize this as the Fokker-Planck equation. And you can also use text or vector guidance on this data generation. You say, I'd like the image to have certain characteristics, and I'll tell you exactly how that is done. So a few years ago, denoising diffusion probabilistic models were used to reconstruct images in the following way. So suppose you took images on the left and added Gaussian noise in a series of steps. And let's say you tried to reverse that process. So you took noisy images and then you gave as a desired output the slightly less noisy image. I mean, could you train a neural network to denoise an image and put back into the image the things that were likely to be there? Now, although that sounds ridiculous because there's nothing there in the original image, if there is a notion of what the distribution looks like for normal faces or normal objects of a certain kind, you can force it to create images that belong to that class or category. So you won't just generate anything, but you'll generate things of that certain category. So what the people working on this did is they wrote down a stochastic differential equation there at the top that described the addition in a series of steps of noise to an image, and then a so-called reverse process, the inverse stochastic differential equation, that would restore the image to its original content or something like it. And this uses a score function. So the score function is the gradient with respect to the image parameters of the logarithm of the density of the probability of the image. In other words, you're trying to make a realistic image. The problem is we don't know how probable the image is. It's very, very difficult to tell how probable an image is, whether it's a reasonable image or not. So if we could do that, we'd be done. But it is possible to estimate what this function shows here, the score function, which is its gradient. And so just looking at that, it was possible to write PDEs that use on the upper right this so-called score function to restore the image. So why does this work? So if you imagine a space of probability distributions, and so if the data comes from a certain probability distribution, which is shown in red there, you can imagine given the current data set, how we can nudge it towards the characteristics of real data. And you could nudge it along the gradient of the log density of the data distribution with respect to the image, as you've seen here. So this diffusion theory allows you to condition the generation. So you could say, I'd like you to restore the image to be a realistic image, because we've trained it to know how they look. But we could also use a steering term, a guidance term, where we obtain the gradients of the weight parameters with respect to a classifier that's trained to recognize images, either Alzheimer's patients or controls, or a certain type of object in the image. And that'll cause the generation of objects that look like that class of things, either Alzheimer's patients or people of a certain age, or a particular photograph. And those of you that are familiar with statistical physics will say that in parallel with the update rule for the image, which is called the Langevin diffusion equation, there's a corresponding update rule for the data density distribution, which is called the Fokker-Planck equation. And you can see that as these are trained and the noise is reversed, the data distribution itself resembles the distribution of the model. And one of the things is the noise in these models. The noise that is added during training and testing allows you to create a diverse sample of images. But very often you don't want it to change the image very much. If you want to age progress an image or heal an image, take a patient's image and see what it looked like when the patient was healthy, you don't want to generate other people's images. And so one of the ways that has been done is using DDIM, or denoising diffusion implicit modeling, where the stochastic term in the reverse stochastic differential equation is turned off. And you can see that this will take an image, either age it or reverse a disease. And then the difference between the input and the output can be used to identify lesions or pathologies, much better than VAE, which will just light up everything. So this type of disease reversal diffusion model can be used, as in this paper by Nikhil Dinagar and colleagues, to make a counterfactual image, an image of what the patient would look like before they were ill, or perhaps even with a certain treatment, by accessing the data distribution and covariates that are associated with it. Now, how are they validated? Usually, well, you've made an image, but how do you know that that's reasonable? One of the ways that these generative models are validated is within subject longitudinal data. So if you have many, many time points where an individual is scanned, you can check whether it's interpolated or extrapolated the brain trajectory in a reasonable way using standard metrics of error. You can also test if the generative distribution of images that are coming out resembles a real distribution. So you can get a set of fake images and a set of real ones. And using generative adversarial networks, which are essentially classifiers of real versus fake, you can tell how well the generator did, or you could even pair up the adversary and the generator in a GAN to have it keep adjusting how it generates images so that the adversary is no longer fooled. And there's a tremendous theory of how these GANs should be designed. I'd encourage you to look up work by Arthur Gretton on MMD and reproducing kernel Hilbert space theory, which talks about why different sources of adversary and different divergences work in the context of training GANs. Let's talk for a minute about other types of data you can use generative AI for. So here's the Connectome. It's been derived from a diffusion MRI scan, and the geodesics of most rapid diffusion are the streamlines or potential fiber tracts. This work by Wendy Feng in our lab and Branch Shangio in our lab uses an autoencoder to compress the streamlines. And one of the things that compression techniques do is they get rid of noise. And in the context of geometric objects, such as these tracts, here shown in this very nice book on human brain connectivity, you can take noisy input data and clean it. And so if you pass the output of your fiber tracking on the left into a variational autoencoder, it will, by compressing the data, eliminate things that don't matter. And this is very valuable. Early approaches, such as this one called FiberNeat, used classical dimension reduction approaches and embedding space outlier detection to trim off the outlier streamlines. But you can now use so-called convolutional VAEs, which type of VAE, to tidy up these streamlines. And you can also use them as normative models, because if it can find outliers, it can also find abnormal deviations. And this paper by Wendy Feng on deep normative tractometry is using deep embedding of fiber geometry to detect subtle and distributed abnormalities in the brain. That's the paper. It's available for you to use if you want to. Another type of generative AI is neural style transfer. So maybe you've heard about cycle GANs or cycle consistent generative adversarial networks. So you could have a photograph like the one on the bottom and want to change it so it looks like a Monet painting, or you could have, if you're an artist, a Monet painting that you'd like to look like a photograph. And you can use generative models to do this so-called style transfer. Now, in the context of medical imaging, you could use this to enhance an MRI scan. You could make it look like it was collected on a different scanner or a better scanner, maybe if you want to harmonize data from multiple sites. And just to explain how this works, style transfer or neural style transfer is extremely interesting. So what you do is you feed in the image whose style you want to change. That's the content image on the left. And you feed an image that has the style that you want, which is over on the right. And you would like to output an image, which is the one in the middle, that matches the content of the image on the left and the style of the one on the right. And it turns out that that object detecting CNN, the VGG19, has layers in it that encode the style. So it's an extremely interesting application. If you fed an image of a sports car and a painting into the VGG object detection CNN, it turns out that the style of the image is encoded in the layers, and you can pull it out using something called the Gram matrix. So let's say there's layers of the CNN that are interpreting those two pictures at the top. They have different channels. So each layer of the CNN might have different channels, different features that it has detected. And if you compute the correlations among these features, it turns out that it encodes the style. So the Gram matrix is something that you compute to represent the style. And then when the neural style transfer method is generating images, you say, we want to do gradient descent on the following penalty function. We'd like the image to look like it has the same content as before, but the mean squared difference in style between the generated image and the target is as low as possible. So this is a really quite wonderful approach. It's been adapted by Mengting Liu, Neda Jahanshad, and Ho-Sung Kim to a generative adversarial model for harmonizing MRI. And you can see that style transfer is very, very important. I mean, you could basically take multi-cohort imaging data and harmonize all of it using neural style transfer. These methods are available. You can run them on your images and match their appearance to certain standard cohorts. This paper by Surabhi Sinha shows that the classification of Alzheimer's disease improves in accuracy if you do style transfer using GANs on the input images. So it's very, very valuable. One caveat is that if you want to disentangle the contrast of MR images from their content, you could also do it in a way that disentangles the geometry and the contrast. And this work by Liu-Henri Zhuo and Jerry Prince, they emphasize that when you train style transfer, you should probably train it on images of the same person scanned with different contrasts. And they emphasize that if you train it in that way, it won't disturb the geometry of the brain. I mean, you obviously don't want the image to be improved, but also, erase some of the important brain features as well. So this is another such approach for disentangled style transfer called Calamity. Another application of this is to create kinds of images that we can't currently create. So let's say we wanted to create an amyloid-sensitive PET scan using T1-weighted MRI and FLAIR. Why would you do that? Well, MRI is cheaper, and not everyone has access to a amyloid PET scanner. And an MRI-based estimate of amyloid burden could allow screening of large numbers of people. So this is work with Yangen and Biogen. So what he found is that by training a neural style transfer model on paired MRI and PET data, where you know the answer, it could generate realistic synthetic PET data for people that hadn't had such a scan. Now, these methods work if there's some mutual information between the signals on the left and the signals on the right, and they're very attractive ways of both enhancing images and generating new contrasts that we can't currently generate. Just some examples of machine learning projects in multi-site neuroimaging data. I'll go through a few. So in our Enigma consortium, which is a multi-site neuroimaging consortium studying over 30 different diseases in 45 countries, the most challenging disorders to detect have been the disorders ADHD and autism spectrum disorder. And I'll tell you a little bit why they are difficult. Most of the study sample sizes of ADHD and autism are rather low. There are good public data sets, but they're not large. And as soon as you test the models on more diverse data, the performance goes down. I mean, either they've been overfitted to the data they have been trained on, or maybe just the diversity of the disease is very high. So one of the ways into this that was suggested by Yanli Zhang James and colleagues is to use autoencoders to embed summaries of the MRI, DTI, and resting state features. And they had found that pre-embedding of MRI features using VAEs before passing them to a standard machine learning architecture, such as a support vector machine, or a fully connected neural network, such as a multi-layer perceptron, was the best. It's still not great, but the unimodal classification just based on one type of image was not very good. And so we're using this. Another computer scientist and psychiatry researcher, Shi Zhu at Columbia University, has very nice papers on using variational autoencoders to embed derived features into latent spaces. You can run free surf raw feature extractors and then embed the numeric values, and then pass those to an MLP, multi-layer perceptron, or other method. And this will tell you not just which features are best, but which modalities are best. And so in identifying people with post-traumatic stress disorder based on their imaging, she found that DTI was actually not very helpful, but a fusion of T1 weighted imaging and resting state imaging was very good indeed. Taking this into the future, Xiaogan Yan and his team in Beijing have been training vision transformers, this version is called an informer, to encode the time series of functional MRI and predict the next frame. And so you can predict brain activity from sequential data in much the same way as you could predict words in language using a transformer. And once trained to do so, it can be trained to also classify mental states, like the percent of the time someone is ruminating or depressed. And so this notion that you could read out at least the mood, if not the content, of the person's mind is tremendously valuable. One application would be to try and find features that forecast good response to treatments such as transcranial magnetic stimulation in major depression, using a mathematical encoding of the brain patterns in each individual. So just to summarize, a lot of these methods are now being used in radiology departments. They don't tend to use functional MRI, but they do use a lot of text, a lot of images, and even tabular data. And one approach is to embed each of them, maybe using a VAE or something else, and then at the last layer, combine them using a more conventional machine learning technique that would allow you to single out what modality of data was the most useful. What should we be careful of? So just to wrap up, I want to talk to you about a couple of problems with deep learning methods that make them fail. One is shortcut learning, where AI locks onto confounding features and won't generalize. Domain shift is where the AI method doesn't generalize to new data from new groups of people, new scanners. And then there's algorithmic fairness. I mean, an AI could work well for some people, but not for everyone. So some solutions include very diverse training and testing. I mean, you could join Enigma if you want and use very diverse data to train your methods. But you can also deliberately use deconfounding techniques, and I'll tell you what they are. So Richard Dinger and colleagues, including Andre Marquand, said that the most common method to control the confounding effects in a model is to regress out the confounding variables. This is what we do in general linear modeling. And you could do that before applying machine learning. You could detrend the variables for confounds. The trouble is that method is insufficient in deep learning because machine learning models can learn information from the data that cannot be regressed out. So one of the solutions that's been proposed by Killian Pohl is when you train a neural network to make a prediction, you also use a subnetwork, an adversarial subnetwork, to make sure that the features that are being used are independent of a certain confound. So let's look at this diagram. If you would like to only use features that are independent of the scanner, you could train a variational autoencoder, such as this one here, with a special gradient reversal layer, an adversary, there on the bottom right. This is work by Aisha Dinser. And the adversary tries to tell what scanner the data came from. And if it can do a good job, you can adjust the feature embedding that goes from the input data to the embedding to fool the adversary. And similar work has been done by Dan Moyer and Greg Versteeg and others. And this is called an adversarial deconfounding autoencoder. You can try and create a feature set that is useful. It encodes biological signals, but it's deconfounded. It doesn't differ when you use different scanning protocols. And this is tremendously useful in making methods more robust. A generalization by Nicola Dinsdale and Anna Nambaretti at Oxford University co-trains neural networks when they're classifying, for example, Alzheimer's disease. You have subnetworks say which scanner was used or what is the sex of the individual. And you try and unlearn these confounds by making feature representations that make it impossible to predict what scanner is used. And then you get a trained model that should be useful on any scanner or new data set. I did want to close by mentioning federated learning. So this is an area which is very, very hot topic right now. Spiros Barkas and his team at University of Pennsylvania have a very famous tumor segmentation challenge where people around the world, radiologists, label brain tumors, and machine learning models are trained to label these automatically. And they're trained on data that's not centralized. So these are trained on data sets that might be all over the world. And there's special methods to do this. So this work by Jose Luis Ambite and Dimitri Stripelis trains a deep learning model to predict, in this case, the age of a person, but it could be their diagnosis, without ever centralizing the data. It just sends the model around to different sites, updates the weights in a way that improves the error on each data set, and aggregates a model by visiting data rather than having it all centralized. So this is a very exciting new direction in federated AI. So just as a summary, there are two types of AI that we've given a guided tour of today. Discriminative AI is used for advancing disease detection, in our case with neuroimaging, but it could be other input data, maybe genomic or blood test data. And there is a zoo of methods being benchmarked. We talked about convolutional neural networks or CNNs. There's also vision transformers, recurrent neural networks called LSTMs, long short-term memory networks, and many hybrids of these. So you'll see a vast landscape of scientific work that is hybridizing and combining all of the best methods into new and interesting architectures. Just before we get carried away, explainable AI can show the features that are being used. So when a neural network has been trained, you can run it with occlusion or gradient sensitive techniques to reveal the features that were useful. Whereas a different branch of AI concerns image generation. And so once again, if you have a set of data with a certain statistical distribution, you would like to train a model to generate new data that is similar in all respects. And in fact, adversarial methods try and encourage the data generator to create images that are realistic. And we talked about how you condition these generations to be satisfying properties that we require, either being healthy, so we can subtract the patient's image from a healthy one, or in the context of neural style transfer, we can make new image contrasts. What should we be careful of? Well, care is needed to model confounds. You don't want a machine learning method to identify something that has nothing to do with a solution. And you can avoid shortcut learning by using adversarial methods for deconfounding. So if you think that the patients with the most severe diseases just happen to be scanned with a certain imaging protocol, you can use an adversarial subnetwork to essentially adjust the features that are used such that you can't predict the site of origin of the data, and that leads to a much more robust neural network. If you would like to test your methods on diverse multi-site data, you can join Enigma. This is Enigma, and there's the website. If you've not signed up, you can sign up to learn about the projects going on in Enigma. And the people scanning as part of Enigma are all over the world. You can see many of the people scanning here. So this would be a tremendously valuable data set to test different AI methods. Just an acknowledgement, much of the work that we've covered today was supported by AI for AD, which is an NIH grant with people developing AI methods at 12 sites across the US. Some of the work was done by Enigma, which is a consortium that we support here in Los Angeles. And we want to thank all of the funders, both in the United States and overseas, private and public, that have provided funding for both Enigma and the AI efforts that we've talked about today. If you're ever in Los Angeles, come and see us. Here we are in Marina del Rey, and we'd be very, very happy to see you. And this is a map of the Enigma members. All right, thank you for your time. Appreciate sharing your time with us this morning, and hopefully we gave you a bit of a taste of the AI methods that are being used today in neuroimaging. Have a good day.